Hi, my name is Afonso. I'm going to present our joint work with Sixiang and Elaine on EnigMap, external memory oblivious map for secure enclaves. So one of the motivating applications for our work is Signal's private contact discovery. So Signal has a database of all their users, and they want to allow clients to query the database with their contact list to check which of their contacts are on Signal. But the clients don't want Signal to learn who are their contacts in their contact list. One strawman solution to do this could be we can have a database inside of an enclave, and we encrypt the communication between the enclave and the user, and this would be problematic because the access pattern on this database would leak the contents of the queries. For instance, if two different users query about the same contact, they would have the same access pattern, and therefore we need to write algorithms that don't leak information based on the access pattern. Even simply permuting the data would not solve the problem, and we need this line of work called oblivious algorithms, which are algorithms whose access pattern does not leak information about the data being processed. Signal initially implemented a batch linear scan solution, so they do a linear scan of the database for every query, and this is extremely inefficient, and they needed 500 servers. And last year they deployed a new solution based on Oblivious algorithms literature, which allow them to only use 6 servers. And these oblivious algorithms and trusted hardware in general are needed everywhere, also in the blockchain space. There are several networks and MEV extractors that want to use SGX enclaves, and they want to guarantee to the users that they are not learning information about the data that's being processed. Our work that I'm presenting today is an oblivious map, which is basically an oblivious key store that's running on a server, and clients can make queries providing 2 properties. First one is query privacy, so the client does not leak which keys it is querying, and the second one is database privacy. The database is kept private. We are going to be running everything inside of an SGX enclave, so the oblivious map is inside of an SGX enclave, and just like we explained before, the instruction memory trace should not leak information about the private data. This means that we cannot have conditional branches based on private data, and we're going to heavily rely on this SIMOV instruction. At last, SGX has a limited amount of EPC-protected memory, and to access external memory outside of the enclave, we can let the operating system swap pages for us using the WB instruction, or we can manually encrypt pages that we want to move out of the enclave and use ocult to do that. We actually started by doing some micro benchmarks, and we found out that OCal was slightly more efficient than EWB, but more interesting, OCal was 46 to 60 times more expensive than just moving pages inside of the enclave. And what this tells us is that external memory page swaps are an important metric for SGX algorithms. So we not only want to minimize the number of instructions that we run, but you also want to minimize the number of pages that we're going to move in and out of the enclave. And in typically algorithm or ORM literature, we take the word RAM model, where we assume that we read and write bytes, and that the compute overhead is similar to the memory overhead. But when we get to this model of secure enclaves, we found out, based on those micro benchmarks, that it would be more suitable to use the external memory model, where we read and write things as pages, and we see the memory inside of the enclave as a large cache. And whenever we need to read and write pages, we have a large cost that comes from system calls, encryption, and possible disk swaps. And in our work, by focusing on minimizing the number of external memory swaps, we were able to achieve a 10 to 100 times faster algorithms than previous work. So we greatly reduced the cost of the amount of page swaps, which improved the performance of our algorithm compared to the previous Oblivious map, which is Oblix. So our contributions were we designed and implemented an EnigMap, an Oblivious map that is both instruction and memory trace oblivious. And we improved the asymptotics of external memory, which resulted in a 13 to 50 times faster improvement compared to previous work. We also provide an improved initialization algorithm. Our solution is based on an Oblivious AVL tree that was proposed in this Oblivious data structures paper, and we use ORAM, pass ORAM as storage. And our main contribution is that we optimized for external memory model. So just some quick background. So we are using an AVL tree, which is a binary search tree, and each node corresponds to a key. And the main two properties that we care about is that for an AVL tree with n nodes, we have a fixed maximum depth, and all the operations that we care about starts from the roots and follows some path to a leaf. Because we cannot let the memory trace leak information, just running normal memory accesses to get a certain node is not possible. So what we need to do is to store the nodes in an ORAM that hides the access pattern to the nodes. I'm not going to go into details on how pass ORAM works. The key points here is that we have a full binary tree with n leaves, and the nodes are going to be present in some of these leaves. And whenever we want to access a certain AVL node that's going to be stored in the pass ORAM tree, we need to provide in which path from the root to the leaf that node is present. And this works great with an AVL tree because we can keep track of the position of the nodes that we want to access by storing the position of the children of a certain AVL node inside of metadata of the parent. Yeah. So nodes are going to be stored or AVL nodes are going to be stored in this ORAM tree, but it's possible that not all the nodes can be cached inside of APC, and we were going to have to use external memory to move them to the SSD. The key optimizations in our algorithm are a locality-friendly layout for the ORAM tree, and this allows us to improve the performance of search and insertion, and a new initialization algorithm for the AVL tree that has asymptotically optimal initialization cost. So in terms of the locality-friendly layout, the main idea is that whenever we read paths from ORAM, we always read the full path. But the way that the pages are stored in disk or outside of the enclave is we can have several pages, several nodes that fit inside of a page. And so we want to try to pack nodes such that when we read a path, we read the minimum number of pages. So we store the buckets in subtrees, and this allows us to, whenever we read a path in ORAM, we need to read a smaller number of pages from external memory. We did some optimization. We did some experimental optimization to try to find out what is the optimal page size for the bucket for these pages, and we found out that it was around 4 kilobytes. Another thing about this layout is that it provides an implicit Merkle tree. I'm just going to skip this in details. So the second part of our key optimizations is the initialization algorithm. So how can we initialize the database if we already have n key value pairs in plain text? And the naive initialization would be we just do n insertions on the AVL tree, but we can actually do better. You can read our paper for details. But the main challenge is that we need to build both the AVL tree with the correct positions, and we also need to put all those nodes in an ORAM. We got optimal asymptotical results, And in our implementation, we also have other non-asymptotical, just concrete optimizations that you can find in our paper. So in terms of experimental results, we analyzed Signal's private context discovery, and we analyzed our initialization algorithm. So in order to create a database with size n, we compared our solution, we compare Signal's linear scan, and we compared with previous state-of-the-art, which also is using an AVL3. And the result is basically, compared with Signal, we can achieve asymptotical speedup, a very large asymptotical speedup. So for a database size of 2 to the 28, giving Signal an advantage by picking a very large batch size, we get 15x speedup, and at 2 to the 32, we get 132x speedup. Comparing with the previous state-of-the-art, we also get higher speedups. And comparing with the new Signal version that was released concurrent with us, we also get a smaller speedup because they're also using optimized alias algorithms. In terms of the initialization algorithm, we did similar experiments. So we're trying to initialize a database of a given size. And we are comparing with Oblivious initialization and with our naive initialization. And in general, we achieve 2 to 8 times speedup compared with the better of the other two solutions. So this project is included as, so this EnigMap project is included as part of our Oblivious data structure library. So it's an open source Oblivious algorithm library. We make all the algorithms there memory and instruction trace oblivious. So they can easily be used in enclave code to make enclave code more secure. And we try to make everything external memory efficient. So the key takeaways from the presentation is that efficient trace oblivious algorithms are possible and crucial for enclave security. External memory is an important model for enclave algorithms. And we could see that by focusing on improving external memory performance, we achieved 13 to 53 times speed up compared to the previous state of the art. You have some results here and questions.